Hello, everyone. Thank you for being here. Today is my absolute honor to present this work. This is work done by myself and a lot of our colleagues in the research group, as well as the product side of Microsoft, the Azure Data team. And it's been a fun, long project. So let me start with a little bit of a journey of the way I see the big data scheduling technology in the last 15 years or so. Around 2003, we all read sort of the MapReduce papers, and there's been a lot of excitement. And in open source, kind of Hadoop was born. Started with a centralized scheduler and supporting MapReduce as the one and only framework we could run on a cluster. At Microsoft, we did sort of something similar, nearby roughly the same time. But the focus was on Dryad, a bit more rich, sort of DAG scheduler and scope as the query language on top of it. Also, the overall resource management was a centralized scheduler. I think what is very interesting, though, is what happened in the following decade. The evolution of these two systems has been radically different. In open source, we focused on fundamentally expanding the set of frameworks we can run on the same system, right? So one of the big steps has been sort of moving on to Yarn. We published a paper in SOC 2013. And along with that, sort of the expressivity of the language, more and more sort of ways of deciding how to allocate resources, some security work. Inside Microsoft, the direction has been completely different. We worked towards making Scope, the one framework we had, better and better. So very good optimization, great tooling around it, very, very rich surface. And to make it scale way, way more than what was happening in the Yarn space. And at the same time, since this cluster got to be really, really massive, and I'll give you some numbers soon, we really had to get utilization right. We really have to get the best out of these resources because we were spending billions of dollars in hardware. Around 2013, our team was tasked to basically figure out, OK, how we get both of these things to happen on the same hardware. We want the multi-framework, the ability to run Spark and TensorFlow and any crazy new thing that community like NSDI will invent. We want access to all of that, right? We want the open source goodies. But we also want to keep the great scale, the great utilization, and the fantastic tools we build internally. So how you go about it? And we spend the next 5 years or so tinkering away, writing paper, thinking things, writing open source code, and deploying things in production. And we came up with a system that I'm describing today, which we name Hydra. So just a little teaser. In the last few years, we've been deploying Hydra in production. And the curve here is basically the number of machines we had running Hydra. Near the top of the curve, we are around 250,000 servers that are currently running this code. The vast majority of our tenants have been migrated onto this platform. We run about 500,000 daily jobs. And it's the first time I was able to write in a paper that was zettabyte, not as a joke. So we actually processed about that much data by the time we were submitting. And about 1 trillion tasks has been scheduled in the meantime. So what are the challenges in doing all of this? Well, the first one is the one we know, Yarn, multi-framework. How do you separate the resource management from the jobs, from the application tier? On top of that, at Microsoft, we had a large number of new applications that were being born targeting these environments. So we want to make it easy, and we did a bunch of work around Apache Reef, top-level project in Apache we started. And then we wanted to get the same level of utilization we were getting with our internal distributed schedulers. So we've done work around opportunistic containers. Costas, that is here with us today, has been spearheading that work. And finally, we had to really tackle scale, right? Sooner or later, you really need to get to this full-size scale. And that's kind of what we are going to be describing the most in today's presentation. Everything I describe has been published about, has been open source, and is in production. So if you have curiosity about these things, you can access pretty much everything. So let me get a little bit more precise of what we mean with scale at Microsoft for this big data cluster. Each one of our cluster is up to 50,000 nodes and up, right? Individual jobs can be as big as 2 million tasks and several petabytes of input. At the same time, tasks have a very broad range. Some of them runs for hours, but some of them runs only for seconds. In fact, the 50th percentile was down to about 10 seconds when we were in the middle of our work. It's a little higher now, but still within seconds. And we were doing all of this at an average fleet-wide, month-long average CPU utilization of 60%. And in particular, for the hardware, we're more familiar with the one we've been running for a little longer. We're around 80, 85, 90% CPU utilization. So we kept that utilization really high. And that meant pounding on the scheduler. In fact, it was a distributed scheduler, so it was not hard to do, because we had lots of independent components that were making those decisions, right? So we had about 70,000 query per second, or scheduling decisions per second, as a sustained rate, with peaks much, much above that. So, what we learned so far in the past is basically, if you need to scale and you want utilization, go distributed. If you want very tight scheduling control, you want multi-framework kind of features, you should go centralized. But we kind of want it all. So what do we do? Our take on it is that you got to federate, right? You're going to take kind of an in-the-middle approach and try to get the value from both worlds and figure out all the details in the middle. So let me describe the architecture that you will build if you want to build a federated system. Imagine each one of these little gray blocks is one of the servers in one of these 50,000 node clusters. We want to break it down into subcluster, partition it into subcluster. Each one of them could be 2 to 5,000 nodes per subcluster, so it would be a standardly large Yarn cluster to begin with. And it will be completely owned and run by a single Yarn resource manager. On top of it, you want obviously visibility of everything that is happening. So we introduced a component called the state store. Each one of the RM heartbeats into the state store, reporting so statistics about what's happening inside the cluster, which applications are running, so general high-level stuff. Now, obviously, we don't want to tell our customer, hey, you remember there was one big cluster, now here are 20 smaller clusters, go figure out where to run. We want to hide all of these behind some abstraction. In this case, we introduce a notion of a router or a software component that looks and feels like a single giant cluster, but it really hides behind multiple RMs. So the request will show up at the router. The router will run a policy that determines which subcluster should we start his job in. And the resource manager does his usual job. It decides which node we're going to start the application master on. The application master is the standard sort of head of this job, the control head of the job. And if we stop here, well, we made it transparent to the user, but the applications are now bounded within a single subcluster. And if you think about it, I just told you that we have 2 million tasks in some of our big jobs. And in general, you don't want to fragment your capacity because you're going to get load imbalances. So really what we need to do is to hide also the fact that there are multiple RM to the applications. And we do this by introducing this AM RM proxy. This is a component that receives application from the AM, runs a policy that determines how to split them, and forward them to multiple different resource managers. So at this point, each of the resource manager can run his own separate local scheduling policy to determine whether the application should get a container, on which machine we should run this container, and the task finally start. And now the task can talk with the AM. And we have jobs spanning the entire fleet, the entire 50,000 nodes. Now, I mentioned the word policy 3 times, talking about the router, talking about the EMRM proxy, and talking about the RMs. And really what we could do, we could simply say, hey, work really hard, figure out what are the good policies that will determine what is a good scheduler behavior, and set those policies. So we realized pretty early that it's incredibly hard to get those policies right. Get the static parts of the system, these pipes that I described right, we could do. But figuring out the dynamics, like how the application will demand for capacity, how will load balancing will flow around, really hard to do. So we introduced a component called the global policy generator. This component stares at the state of the cluster, talks with the various components, analyzes the content of the state store, and can determine what is the overall set of policies that we should run, right? And it can dynamically push policies into the rest of the system by writing them in the state store, and the various components will learn from the state store what is their role in this orchestrated overall behavior. And at this point, I should tell you something about policies. So let's look at the policies. Oh, pardon. So overall, when we do scheduling in this environment, we definitely want to shoot for really, really high utilization, right? Again, infrastructure is really expensive, so we want to get high utilization. We want to get some form of scheduling invariant, some property of your scheduling. Fairness is a very common one. And again, think about some of our customers are very big, are Bing or Windows or Azure, and they maybe spend $100 million with us. They want to get their fair allocation of the resources, since they pay for it. And locality, it's quite relevant. There's been big debates around whether locality matters or not. Just to keep it very simple, some of our clusters span data centers. The moment you start spanning cross data center, you definitely need to pay attention to locality. And there's a bunch of other reasons why you may or may not want to care about locality. And locality is typically expressed by the application that says, my data is there, please run me on that machine. Or I want the kind of hardware that exists only on that machine. So let's take some example of simple policies. Let's look at the EMRM proxy and the RM. One basic decision is, shall I enforce locality in the EMRM proxy or not? So when you ask me to run somewhere, shall I forward this request just to the RM that owns that machine, or shall I spread around your request to everyone else? That's one policy choice. Another one is, at the RM, shall I be very tight and enforce quotas and not allow you to go above your quota, or shall I allow you to go above based on just my local view of the world, right? So again, shall I enforce these quotas tightly or not? And if we take an example, say these two little queue, 50% of the capacity for QA, 50% of the capacity for QB, two subcluster, and imagine that the queues are mapped evenly between the two subcluster. The demand will not be necessarily be even, right? It depends where the data is, depends what the application wants to do. So I'm, for example, describing 12 container and 12 container for QA across the two subcluster, and 4 and 12 for QB. So let's say that we start by enforcing locality and tight quotas. Great. What we get is very good locality, very good fairness, but we get bad utilization because we have a few containers in subcluster 1 that are not allocated. The second thing we can do is to say, well, then just let the subcluster 1 over-allocate, right? Go above quota if there is demand from one queue and not the other. And if I do this, it's very good for utilization. I get good locality, but my fairness is now disappear, right? So, well, then I can tell the EMRM proxy, hey, spread this load more evenly across. So giving up some of the locality, but you're going to get good utilization and good fairness. And that's correct. But again, we're giving up locality. Obviously, you understand that there is a solution for this problem, right? We should over-allocate in subcluster 1 for QA and under-allocate in subcluster 2. But to do that, we need sort of a global point of view. And I made a big case around the fact that we have this big scale, 70,000 QPS. We can't really do everything centrally, right? One fallacy is that we're trying to solve sort of two problems at once, right? We're really should be solving shared determination, which is the question of how many resources should we give to each one of the queues, separately from the problems of placement. Where should we give these resources, right? Where each container should be running, right? And the key intuition is that we can actually decouple these two problems and get a little bit the best of both worlds. A proposed solution, and the asterisk says that this is a bit more rich than what is actually in production today. If you care for what's in production, look at the paper or talk to us offline. Goes as follows. Each one of the resource manager will take the stock of what is the status of their queues locally to their subcluster, how much demand, how much used resources are there, and we'll send this summarized view of the world to the GPG, the Global Policy Generator. Over there, we can run an algorithm that fundamentally does the logical work of taking the entire cluster capacity and logically reassigning it across all of the queues by paying attention not only at the fairness at every level of the hierarchy, but also at where demands exist, right? So we're going to try to match the demand with the locations, right? So if there's a lot of demand in subcluster 2, we're going to give B more containers there, but then we're going to hold B accountable and keep it down on subcluster 1, right? So we can create that imbalance locally that create the global fairness and a full utilization. And while doing this, obviously, we also paying attention that if there are already assigned resources, we should try to match that location so that we don't create unnecessary preemption. And when this is done, we can send down to each one of the RMs sort of marching orders. We'll say, this queue on your subcluster need to get this many resources. Now focus only on the problem of task placement. Like all the rest is solved for you, right? You can just go ahead with that. And if we do this, of course, the resource manager can locally figure out their allocation of resources, and we solve the overall problem. Now, I sweep under the rug a problem. The reason you don't want to do things centrally is not just scalability, but it's also because you don't want to introduce single point of failures. If we have a single point of failure like the GPG, and the entire cluster doesn't get scheduled, well, we're throwing away hundreds of millions of dollars in hardware just because one machine is not doing its job. Well, we can deal with that. The GPG downtime doesn't really mean we don't schedule containers. It just means we cannot enforce fairness tightly, right? We can allow each one of the resource manager to keep giving away containers at the full rate, The problem is that if we don't hear from the GPG for an extended period of time, we will slowly drift into one of the sort of local incorrect views of fairness that we described in a few slides ago. We can do a little bit better than that. So this basically means we can survive without the GPG for a little bit, provided the GPG comes back online. It's a reasonably stateless component. We can recover quickly. We should be OK with it. In fact, we can do slightly better. We can leverage, in this case, LP-based algorithm that tune the baseline queues in each one of the clusters. So by looking at history. So in the example I was making before, instead of giving the queues 50, 50, 50, 50, I can start by saying, well, QA gets 75 and 25, and QB gets 25 and 75 across the two subclusters. This way, naturally, the local decision made by the RAM will tend to converge towards what is the global fair behavior. Of course, if the current load is comparable to the historical one we have seen. And this is just a way of ameliorating the problem. Let me jump into looking some experiment if you want. Fun thing of doing experiment when things are in production is that you just open a bunch of dashboard and pull down the numbers from there. You think it's easy, and then you have to fight with getting the right number, getting the right scale. We're missing some data in some telemetry. But we have done all that. And this is simply the things I'm going to report are sort of Microsoft-wide production workloads. There's about 5 clusters that I'm presenting here, about 250,000 machines, half a million jobs, about 2 billion tasks daily. There are many more details in the paper, but the one thing to keep in mind is that the load is incredibly skewed. There are very, very small job and very, very big job, very small task and very big task. Distributions of input sizes of all sorts, right? So there's a large population of about 15,000 developers that are using this system, and they explore pretty much every corner and every way of stressing our infrastructure. They figured it out. So that's kind of what we're dealing with. First thing, we were after scale. Do we get scale? Here I'm showing 12-hour averages, about 1 month worth of data. This is a recent, so it's not what you find in the paper. That's the, at the end of everything being in deployment in the last month or so. And we see about 65,000, 70,000 sustained QPS at the scalar in one of these large clusters. And at the same time, the allocation latency is about 2 to 3 seconds, right? Which is kind of what we want. It's roughly comparable to the 1 heartbeat round trip from Yarn. So it's pretty much in the ballpark of what we expect. Utilization, right? We were trying to do all of this while keeping utilization really high, right? Having all of these multiple framework Yarn-style APIs while keeping utilization high. So this shows a period of about 8 months in which we were deploying very aggressively across our fleet. So at the left, in the July 2017, we have only a small fraction of our capacity has been upgraded to Hydra. And near the end, near February 2018, a large portion of our infrastructure is already to Hydra. So what we see is that throughout this migration, this deployment, we're maintaining the average utilization pretty much at the same level, right? We can't increase it necessarily because we don't have more workload coming in, but we're maintaining it for sure. The nice property of this graph, though, is that if you look at the extremes, they're coming in, right? That means we're load balancing across machines better, right? The fact that we have semi-local, or 5,000 machines at a time, or 2,000 machines at a time subcluster view, it means that we can locally balance across those. And this overall indicates that we have a better story for load balancing cluster. And there turned out there are some effects also on task latencies that are also desirable, or efficiency with which task process that are also derived from this. Finally, customers don't care if their jobs run slower. You could have done the prettiest, most beautiful, more generic solution in the world, and if my job were now running slower, they will be complaining until you fix it or get fired. So we didn't get fired, and we fixed it. So that's the good news. However, measuring this is quite not easy. So what we did here, what we show in this graph, we took recurring job so that we'd have like a comparable point, right? Two runs of the same job, or actually 1 month worth of runs before we deploy Hydra, and 1 month worth of run for the same job after we run Hydra. We took the ratio of this behavior for the runtime of the job, and that is 1 point in the CDF. We repeat this operation for, I think a couple of million instances of jobs. We also discarded jobs that grew or shrank in input size by more than 2x, because otherwise the data will be all over the map. And what we find is that a pretty even curve, right? more or less crosses around the middle, and is a pretty even curve that says some job go faster, some job goes lower, and that's a factor mostly of their input size getting bigger or smaller. But pretty much we didn't affect the job runtime. The second lines, the dotted lines, actually show you the same ratio but for the total computation time of the job. And I separately told you that the tasks are actually just as efficient when they run. So this is actually telling us the job got about 18% bigger at the median, and at the same time, we're running them in the same time. So this tells us two things. Tell us that the scope runtime system can parallelize really well, and Hydra underneath is not messing up the game of scope, and is keeping up by delivering enough parallelism to actually accelerate the job even despite the increase of overall runtime. So this is kind of more on the numerical side of things. There's more sort of a qualitative nature of our experience, some of the lessons learned if you want. This was an in-place migration. You can imagine that a 250,000 machine scale, they didn't allow us to just buy another 250,000 machines and then install the new system and then move over. We had to do everything in place, so flipping servers from one version to another as we were migrating customer. That was an experience, a long and painful one, if I have to say, but overall very interesting, right? As we were moving tenants, different tenants that exacerbate the system in very different ways. So at the end of everything, we have very happy customers. They now have access to all of the open source stack, and as well as Microsoft technologies. The federation design gives us better operability than what we had before. We now can play with each individual subcluster, deploy new versions of the software, test out new innovations from open source, and that's quite good. And finally, we have the policy-driven design. The fact that we had fixed mechanisms and policy kind of be able to change very dynamically was actually very useful to adapt and correct for changing workload, changing hardware, and so on. So in conclusion, Hydra federated design gave us a little bit of what we were after, right? We wanted multi-framework support, we wanted scalability, we wanted utilizations, we wanted operability, and we got there. The journey has been phenomenal. Going from 0 machine to a 250,000 machine has been fantastic. We wrote a lot of code. A lot of it is in production at Microsoft. About 200,000 lines of code got open sourced. We wrote about 11 papers in the process. And if this is the kind of research you're excited doing, like building real system and get them in production, open source them, come talk to us after the session, because we might have a job for you. Thank you.
Hello, Nodir from UBC. Thanks for the talk. I had 2 questions. The first one is, do you allocate network also, or is it CPU and RAM only?
If we do allocate network?
Yes.
It's fundamentally just CPU. Honestly, that's the bottleneck for us. Networks are actually not too badly allocated right now. There's been work to look at the IOs, mostly on the disk side of things. There's been consideration for networks. As of right now, our network infrastructure is beefy enough that, in fact, we're considering to give up some of the locality to get better load balancing on the CPUs. So we're completely packed on CPUs right now. That's the fundamental situation. So I think if you're doing research in that space, I think it's an interesting point. The current state of our infrastructure is such that we don't care about the problem. Okay. Probably because we bought too much network a few years back, right? Very honestly.
Okay, so network is over-provisioned. So the second question is maybe the lines of 11 published papers. So I've seen SOSP 2017 Resource Central paper where cluster size is like 886, so under 1,000. So
those are 2 parts of Microsoft, right?
Oh,
so the Resource Central paper is Azure. The stamp, the size, and everything is designed public cloud. We run under what is called Autopilot, which is more of the internal infrastructure. Okay. There's separate work on converging some of those, but the size of cluster in Cosmos side are much larger. And in fact, using federation, we're even considering to wire together all of our federation in a single sort of intergalactic federation across all of our overall fleet.
Okay, that opens even more questions, but I'll take it offline. Thank you.
Sounds good.
So I have one question. So the scheduling policy that you were describing across RM, so when there are jobs that have some amount of demand in one subcluster and some amount of demand in another subcluster, could the policy be thought of as a variant of dominant resource fairness? Because you're basically saying some job's dominant cluster is A versus some other jobs is B. So you're essentially solving that? Or?
So it is dominant resource fairness for each one of the allocations. But the problem across, I don't see it necessarily as dominant resource fairness. Dominant resource fairness tend to also bottleneck on one of the resources for each side, and we don't necessarily want that, right? We want to try to utilize the resources more fully. I can maybe discuss offline a bit more on the details of what the algorithm does. But conceptually, the reallocation of all of the resources is very much DRF inspired. But when you look at how each queue need to be mapped between different subcluster, you need to play different games based on the demand there.
So I have one more question for you. So with jobs, progressively more tasks become runnable already over time.
Repeat the question, please.
Oh,
You don't have a mic.
this one or this one? Okay. So my previous question was whether their scheduling policy was similar to dominant resource fairness, and he said it's different. My second question is, now I'm forgetting what my second question is.
Thank John. They made it easy.
Oh, yeah, so as jobs run, tasks become runnable already over time, right? And so, I mean, so first of all, I'm curious about how would jobs be able to say, here is what I would need across these subclusters.
So the job don't see subclusters, right?
Okay.
The job see the entire fleet as one whole.
Right.
As a task becomes runnable, it means that its input is available, and that input exists on some machine somewhere. So the scope AM in the case will say, hey, there is for input, I have 3 locations where I can run. Please give me one of those. If it's intermediate data, there will be only one location that says I really want to run on that machine. And the general agreement, this is a soft constraint that says I can run really anywhere. I prefer to run on this machine. If not on this machine, somewhere in the pod or rack where that machine exists, and otherwise run me whenever. Right?
I see. So I guess that was what I was wondering. So it does seem like your demands are somewhat soft in that sense.
It is somewhat soft. The important thing is that at some point you hit a T3, which goes across buildings. And at that point, if we start shuffling some of our very big job across those, we will take down the networks.
Okay, let's thank Carlo once again.